So you can pause the recording and write that down and think about the problem, but I'm going to launch right in. It's always a good idea to draw a force diagram because whenever there's work involved, you want to know what the forces are. So I'm going to draw the forces in this situation. It mentions a snowbank, and presumably the snowbank is exerting a force to stop. It's not really friction. You could call it friction, but there is a lot of friction involved, but let's just call it a generic force F. There's a normal force up, weight down. Those are presumed to be equal. But what's really important is this stopping force from the snowbank. This is the really important force. It's that stopping force. And what we know is that that force is going to be exerted over some distance, d. What matters is that that force is exerted over some distance, d. And that force multiplied by the distance is work done by the snowbank on the car. In this case, think about this for a second. Does the snowbank do positive or negative work on the car? Does negative work on the car because the car is presumably moving in this direction. So this distance occurs in that direction and the force is in the opposite direction. Therefore, we can assume that negative is work done. Negative work is done. Now, the problem asks for the force. So if we look at the relationship and think about how that work is translated to energy, that negative work saps or takes away kinetic energy. So I write down force times distance equals 1/2 mv squared. I write down force times distance is 1/2 mv squared. And I'll just briefly show you where that came from. Basically, it's the idea that the work is equal to, I'm going to put kinetic energy, but because the delta is confusing to people, there is kind of a little delta there. But I'll just put kinetic energy because what that really means is the work became kinetic energy, or in this case, it didn't add kinetic energy. What did it do? Think about that. It took away kinetic energy. So that's kinetic energy that's lost. You plug in. We do know the distance. We know the mass. We know the speed that was lost and became 0. And you plug in and you solve and get the force of 9,167 newtons. And again, this next one, just pause it and write that down. But I'm going to launch right into it. I'm drawing a force diagram. It says you push a crate. It doesn't mention a specific direction, but it doesn't matter. There's a 350 Newton force by you. There's also friction. The friction is going to be really important. There's a normal force and weight, which I will draw, but they're not critical to this problem. However, I should note that if you were given a coefficient of friction, instead of just the force of friction, if you were given a coefficient instead of this force right here, then you would need to calculate it, and then you would need the normal force, and you would need to use the fact that it was equal to the weight. However, in this situation, I made the problem easier, and I just gave you the frictional force of 100 newtons right there. So now that I know what my diagram is like, I'm going to calculate the work done by, I'm going to calculate work by F, and that's going to be really easy to do. And I'm going to calculate work by friction. That's going to be really easy to do. So I just do work equals force times distance for both of those. Work equals Fd. Work is equal to force of friction times d. And if I just calculate, I'm getting out my calculator now, I'm just going to do 350 times 4, and I'm getting 1,400 joules. And stop and think for a second whether or not that's positive or negative. That's positive because the force was in the same direction. And friction times the distance, mental math, 100 times 4 meters, 400 joules. Stop and think whether or not that's positive or negative, and you should realize it's negative. So the logical thing here is, yes, we're going to look at work equaling kinetic energy. We're going to look at work equaling kinetic energy, but the logical thing is not to take just any old work. Just like with forces, you're not just going to grab this number, you're not just going to grab this number. They obviously both play in to the work that was really done, and we call that net work. We call that net work. It's just a total. Net work is just a total. Now, I hesitate to even write net force in there because that confuses people. They think that that's something new or something tricky. It's not. It's just look at the real total work that was done. And if you stop and think about it, I think you'll agree that the total work that was really done is 1,000 joules. That's equal to the kinetic energy, which is 1/2 times the mass times the velocity squared. We are asked for the final speed. The final speed we solve for V. We are also asked for how much energy it gained. And the answer is 1,000 joules for part A. The answer to part A is 1,000 joules is the amount of energy it gained, and that was kinetic energy. Kinetic energy, because it's moving. So now I'm going to solve for V. I'm going to solve for V. And just doing a little bit of mental math, 1,000 divided by 20 is 500, I think.
50.
And the square root is, doing the square root of 500. And square root of 500. Oh, square root, oh, sorry, 50. Square root of 50. 7.07 meters per second. Depending on the sensitivity of the microphone, you're hearing the students gather for lunch.